The cosmological principle binds the mathematical form of any applicable laws. The Hubble's law is no exception. To see this, we consider three galaxies which are subject to Hubble expansion. Suppose galaxy 1 is from where the galactic recession has the form given by Hubble's law. What happens if we make galaxy 2 the center of observation? Would the same form of the law remain valid still? To see this, point two radial vectors A and B from special galaxy 1. If Hubble's law is valid, the recession speeds of galaxy 2 and 3 would be proportional to the distances A and B from galaxy 1. Let us now make galaxy 2 the center of observation. The law of manipulation of relative speeds tells us that the speed of galaxy 3 with respect to galaxy 2 is again proportional to the distance c between these galaxies. Thus the form of Hubble's law is valid irrespective of which galaxy is taken as the selected or chosen galaxy. Note that the law would not have been valid even if the r-dependence would have been anything other than linear, and so it is true that the cosmological principle constrains the form of the laws very tightly indeed. The possibility of cosmological expansion which keeps the cosmological principle must be an uniform expansion. All lengths are stretched with the same factor, otherwise it would mean that space-time is less stiff or more elastic at some points. The key point about expansion is the same scale factor, a, for all points. This is the reason why it is often compared to the expansion of balloons. If space were 2D, it could have been carried on the surface of a balloon. A scale drawn on the balloon would expand in the same way for all pair of points, with what was 1 centimeter this second becoming 2 centimeters on the third second. Unless the balloon is thicker or thinner at various places, which is not allowed in homogeneous cosmology. The remarkable thing in this that the scale factor expansion can mimic Hubble's law. It is not difficult to identify from here that one can get an estimate of the age of the universe from the measured value of Hubble's parameter. It won't be exact, but it would be a value one can simply turn over to as a reference while discussing elaborate matters like the beginning of time. Consider two galaxies which are in contact at the beginning of time. After time t0, which is the current time, they are seen to recede with a speed v and are separated by a distance r due to cosmological expansion, not their fault. If the Hubble parameter would have been constant for all this time, then the age of the universe t0 is given simply as the reciprocal of h0. If we calculate the value of this quantity, it comes out to be of the order of 14 pi. We would see later that the age actually depends on the composition of the universe, but for now, it can serve as a cosine order of estimate. The cosmological expansion stretches the photons and their wavelengths get stretched by the scale factor of expansion. Getting back, we see that the ratio of the wavelengths at the current time, lambda O, and the wavelength of the photon when is emitted, lambda E, is 1 plus z. The wavelengths are proportional to the scale factors at the respective times. The value A equals 1 is valid for the current time t0 when one calls a meter a meter. If the universe was half as large as now when the photon was emitted, A would be 0.5 at that past point of time. And so, the relation between A and Z is a reciprocal one. In cosmology, one often alternates between the scale factor and the redshift, both of them functioning as surrogates of time.